All right, let's talk about something that's literally everywhere. Chance, uncertainty. How do we actually make sense of it all? Well, that's where discrete probability distributions come in. Think of these as the fundamental building blocks for putting numbers on randomness. So here's how we're going to tackle this. First, we'll start with the absolute basics. What even is a random variable? Then we'll lay down the rules of the game, the blueprint, if you will. After that, we'll get our hands on the main tools for the job, and finally, we'll see where all this stuff pops up in the real world. Sound good?
Okay, first things first, we have to start with the absolute core concept. Before we can analyze anything, we gotta know what we're working with, and that is the random variable. So what is it? Put simply, a random variable just takes something unpredictable, like rolling a die, and slaps a number on the outcome. That's it. It's the bridge that lets us take messy real-world chance and turn it into clean math we can actually work with. Okay, now this is a really important distinction you need to get. Random variables basically come in two flavors. You've got your continuous ones. Think of anything you measure, like a person's height. It can be any value in a range. But for today, we're focusing on the other kind, discrete variables. These are the ones you can count. 1, 2, 3. Like, how many heads did you get in 5 coin flips? They're separate, isolated points. That's our playground for this explainer. All right, so we've got our building material, the random variable. Now let's look at the blueprint. There are two fundamental rules that every, and I mean every, discrete probability distribution has to follow. No exceptions. And honestly, these rules are just common sense when you think about it. First, the probability of any single thing happening has to be somewhere between 0 and 1, right? It can't be less than impossible, and it can't be more than 100% certain. And second, if you add up the probabilities of every single possible outcome, they have to equal exactly 1. That just means you've covered all your bases. Nothing's been left out. Okay, with those rules locked in, we can now build our first and honestly our most powerful tool. It's the mean, but in the world of probability, it gets a much cooler name, the expected value. Now, I know, you see a formula like this and your eyes might glaze over. But don't let the Greek letters scare you. All this is saying is that we're calculating a weighted average. You just take each possible outcome, multiply it by the chance of it happening, and then add all those little pieces together. That's it. So what does expected value really mean? Here's the key. It is not what you should expect to happen on any single try. It's the average result you'd see if you could run the experiment again and again and again, literally thousands of times. It's all about the long run. Okay, let's make this real. Look at this table. We've got 3 possible outcomes. You could get a 0, a 5, or a 10. And each one has a specific probability. So, to get the expected value, we just do that multiplication we talked about. Look at the third column. 0 times its probability of 0.5 is, well, 0. 5 times its 0.3 probability gives us 1.5. And 10 times its 0.2 probability gives us 2.0. Simple as that. And now for the final easy step. We just add up that last column. 0 plus 1.5 plus 2.0, and we get our expected value, 3.5. Now think about that for a second. You can't actually get a 3.5 in one go, right? Your outcomes are either 0, 5, or 10. But if you were to do this over and over, thousands of times, the average of all your results would get closer and closer to that 3.5. Knowing the long-term average is super useful, but it doesn't tell you the whole story. I mean, are the results usually close to that average, or are they all over the map? To figure that out, we need another tool, a precision tool, and that's the standard deviation. Yeah, okay, that formula looks even scarier, right? But again, let's just focus on the idea behind it. The standard deviation is all about measuring the spread. It tells us, on average, how far off the results tend to be from that mean we just calculated. So, a small standard deviation? That means your results are going to be tightly packed around the average. It's a really consistent, predictable experiment. A big one? Whoa, the results are all over the place, much less predictable. All right, before we jump into the real world, let's quickly go over some common mistakes people make. Seriously, watch out for these. First, don't assume the expected value is something you can actually get in one try, like our 3.5 example. It's an average. Also, don't mix up the outcome itself with its probability. 2 totally different numbers. And please, 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 always double check that their probabilities add up to exactly 1 and that none of them are negative or bigger than 1. It's a sanity check. Okay, enough with the theory. Let's take these tools we've just built and see how entire, massive industries are literally built on the concepts we just walked through.
Ever wonder how insurance companies make money? It's just expected value. They have armies of statisticians who calculate the average amount they expect to pay out for someone like you. Then they just charge you a premium that's a little bit higher than that number. So for you, the expected value of buying that policy is actually negative. But for them, when they do that across millions of people, it's a guaranteed profit.
And you know who else uses this exact same logic? Casinos. That phrase, the house always wins, the house edge is nothing more than a negative expected value for the player. Every single game, blackjack, roulette, you name it, is perfectly tweaked so that, in the long run, the player is expected to lose a tiny percentage. Sure, you may get lucky tonight, but the casino isn't playing for tonight. They're playing for millions of bets over years, and thanks to the law of large numbers, they know it's a mathematical certainty that they'll come out on top. So that brings us to the big takeaway. Now you know that the house edge is just a fancy term for negative expected value. So my question to you is, what other parts of your world are secretly being run by these same statistical rules? From the stock market to medical trials, these ideas are everywhere, quietly shaping things behind the scenes. Where are you going to spot them next?